Hi, Carl here from Hyrel. I've got a beautiful engine HR, that's high resolution engine, which I wanted to give you an overview on. And to really get into it, I wanted to first go backwards to the motion control evolution. I've been personally moving stepping motors since 1979. We started with 4 transistors and a resistor and a static power supply. And we moved forward in time to where we started using bridge drive circuits for the different poles in the motors. And as we first started making the 3D printers 14 years ago, we were using motor stamps similar to this. And these would have a full bridge driver in them. You would give them step and direction. You could also tell them to give you micro stepping. And what that does is instead of going from full current like this to opposite current, it would take it and give it half current, 1/4 current, 0 current, and back, and that would give you a finer motion. The problem with that is that the stepping motors themselves, this being a stepping motor, which we use, they have magnetic poles, and the magnetic poles, while being good, are not perfect. So they actually have some error built into them. So if you listen to a stepping motor running slowly, it'll go boink, 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 boink. I'm accentuating that a little bit, but it means that the poles, some of them are a little bit stronger than some of the other ones, which gives you a little bit of offset error. Not enough to be significant in the 3D printing world, more than enough to be significant in the CNC world, where ultimate precision is very important. And the other negative thing is when you hear that boink, the extra loud noise, that noise represents a move that's irregular. So when we try to speed it up, that begins to resonate and it actually can stall the motor. And so it limits your upper speed with smooth motion not being smooth. It's actually becoming quite rough. So that's one negative. The other one is this vibration that we're hearing on the stepping motors is actually going to everything in the system, including your precision bearings. And it will cause premature wear on your bearings, and if you're in a CNC world, on your cutters also. Okay, so let's go back over here. We're going to look, and this is the original motor run by a stamp. And then we move to closed loop servos. And a closed loop servo has a controller like this. It sees the drive signals going out to the 2 phases, or in this case, they were 3-phase or 5-phase, in our case 3-phase. And then underneath here is a flat disc with holes in it. That flat disc with the holes or slits in it have encoders that feed it back, and it tells this guy, I have moved exactly a certain amount. And if it can't move, like if you're moving this and it hits a stop, it will stop with a certain amount of torque. It won't keep driving it harder. And then it goes, hey, I am not where you think I am. So in case it's important, you can send an error message. So that's the way a closed loop servo system works. Well, this is a very expensive solution. The stepping motor with a stamp is a very inexpensive solution. And so a few years back, I would say about 6 years ago, we came across a nice project where they had created a board with a special magnet, a magnet that instead of being through the axial was actually radial, which means the north and south pole would go like this. And they have a chip that was developed that's a Hall effect magnetic encoder. And it can read a rotational position in up to 32,000 different positions per revolution. Well, that's way better resolution than what the motor itself can do. It's only 200 steps per revolution in full step mode. In 1/16 mode, it would be 3,600, 3,200 pulses per revolution. And we're talking about 10x that for looking at where this is at. Okay, so why is that important? Well, what's important is this big box with these long cables, which have to route all over your printer, okay, become this circuit board mounted nicely to the back of your motor. Now, that is a huge packaging reduction simplifies the cabling for sure. But the other thing is that because we have closed loop feedback, if I am driving a printer and I get into a stall zone, rather than break something, it will just stop. Now, if it's in a case where we are having a lifting part or something like that, it can sometimes, as you all know, have a layer shift. This will not have that problem because it knows where it's at and it automatically compensates for it as it moves along. Okay, it also makes incredibly smooth, silent motion. We'll shoot a clip of the ESR, that's our standard resolution, which uses these motors and this drive configuration, and you will see it's whisper quiet. It used to go, what? No more. It has for multiple years been excellent, and we're proud of it, and we see the rest of the industry is also adapting these types of drives because they make sense. Low cost, high performance, closed loop feedback, less wear and tear on the machine. So, and it's much more office friendly. If you're sitting next to your printer, it's not driving you nuts. Okay, so that's about the motor drive. We have incorporated this onto our system, and we have 3 drive motors with a closed loop servo in them. They are programmable for current, microsteps, and direction. And so that makes it easy for you to configure your machine whichever way you want to. We, of course, normally have a standard configuration where we test them all, and that's usually the way you print. But once in a while, someone asks for something different from us. Let's look at the reason why this high resolution is so expensive, and you'll understand better. If you could come in a little bit closer on the camera. This is a precision ground ball screw, not rolled, but ground. This particular one is made by Misumi, and we also use IKO or THK, depending on which one we're liking. This is your x-axis, and this is modular, so we can buy and put on an x-axis that's 200, 300, 400, 500 millimeters. And this can more than handle that weight with no issues whatsoever. In some cases, we build an extended x-axis out here, so when we're done processing here, it moves over and allows a second machine that sits next to it to process what you've just printed. Exposure, things like that, maybe inserting something in what you're printing and it comes back and continues on. The screws that we use, so the y-axis we build, and it's machined at a very precise amount and or specification, and we have 2 precision IKO linear bearings with 4 trucks on them. So you have 4 riding bearing systems, and their alignment has to be perfect, but we take care of all that here. Once that's aligned, you have very smooth, stable motion, and the weight is not an issue for us. And that was what was important because we wanted something that could handle the cantilever if we wanted to run this build off of the printer to a second piece of equipment. And so that took care of that. So 2 linear bearings for the Y, 4 contact points to make it extremely stable, a cast and ground steel with ground ball screw for the Y dimension. This is configurable. All of these are being run by closed loop servo motors, okay, servo steppers. Now that gives you an idea of why the precision is so high for this. On the upper side, we have 5 slots here, and let's just run a home thing. The reason for so many slots is that most of the time we print in 2 or 3 of these, or 1 or 2 or 3. And then we put some other apparatus over here, like a microscope. Because most of the time when you're working on this machine, you're working in very, very small detail. And this allows us to put a microscope that looks right at the print. So it gives us instant feedback. We've done some very difficult printing where we couldn't see with our eyes what was going on. We thought it was close, but you know, to dial in the last little parameter, the last 20 or 30 microns, it did a great job of letting us have a fixed camera so we could see exactly right on the tip what was going on. A good example of that is the wax print. You'll see that online. Okay, so that's one incredibly important feature of why this is used. Another thing that we've done with all of these different positions is you can actually mount this up, and this gives you a secondary lifter head, and then you can mount any of your, let's just plug this in here. All right, and now you can mount a head into here, and you can raise it so that there's no collision with the head next to it that you're printing with. And so that gives you a very interesting interaction between two heads that have independent Z capability. So this is another apparatus that's very popular with this. Some people have asked us about placement of parts. We have a pick and place head you can mount in here, and then you can place over here small parts that you would like to pick up and then place down. Very easy to do that. Another thing is that this was built with a special project in mind. If you look online, there's a guy who is a young man, and he has built integrated circuits in his garage. And this gave us an inspiration when we looked at this and said, wow, actually making a computer chip in your garage, one of the things you have to do is lithography. That is the act of creating an image using light patterns. And so he has a really cool thing where he took a microscope and turned it backwards, put an LCD on top, hits it with UV light, and then he reduces down what the LCD is doing, and out comes a much reduced, 100x, 200x reduced pattern of what he would like to actually expose the wafer to. And so in this case, he can do step and repeat. So if anybody out there is looking for doing extremely small patterns on top of an emulsion, give us a shout, because it's actually a really fun project and we're glad to help you with it. Okay, I hope you guys are having a good day, and that's the Engine HR.